Hello friends, this video is all about the next conversion, which is hexadecimal to binary and binary to hexadecimal. So last video was about octal to binary and binary to octal. So with the same procedure, we will make a conversion from hexadecimal to binary and binary to hexadecimal now. So hexadecimal is base 16 value and 16 can be represented as 2 power 4, which means each value of hexadecimal can be represented with 4 digits of binary. So that is the basic assumption. So 0 can be represented in binary with 4 digits as 0000, and for 1 it is 0001, for 2 0010. So similarly from 0 to 9 values, 4 digits of binary are filled, and after 9, 10, 11, 12, 13, 14, 15 are represented with A, B, C, D, E, F, and the corresponding values are filled accordingly. So to fill these values, we know about 8421 rule also. So we can apply that and get the consolidated value. So 8421. So since it is of 4 bits, we can make use of this 8421 to fill the equivalent hexadecimal value. So for example, if the value of 12 is to be filled, then we have to check the equivalent value. So 8 plus 4 will be 12. So under 8 and 4 it is replaced with binary 1, and under 2 and 1 it is 0. So this is the equivalent representation of 12. So as you can see, after 9, 10, 11, 12, 12 is represented by C and the equivalent binary value will be 1100. So this is the equivalent representation. We have to know this table to make a conversion from hexadecimal to binary. Now let us see an example. So the first example is 259A, which is a given hexadecimal, and we have to convert this hexadecimal to equivalent binary value. So first let us segregate the value and write the equivalent 4-digit hexadecimal value now. So 2, the equivalent value from the table can be chosen, which is 0010. Next for 5, it is from the table 0101, that is written over here. Next for 9, it is 1001, and for 8 it is 1010. It is filled from the table accordingly. So if we forget the values, then we can use this 8421 technique. So for example, if it is 2, then we have to replace the corresponding value as 1. So for 2, under 2 we have 1, and the remaining values are filled as zeros. So we get the 0010. Next for 5, it is 4 plus 1 is 5. So under 4 and 1 we can take it as 1, and the remaining is 0. So 0101 is obtained over here. Next for 9, it is 8 plus 1. So under 8 and 1 we have the binary 1, and remaining is 0. So 1001 is the equivalent value for 9. So A is 10, which means 8 plus 2 is 10. So under 8 and 2 we have 1 and 1, remaining 0. So 1010 is the equivalent value. So to write the equivalent representation, we can use this technique. So to write the equivalent binary value for the given hexadecimal, just put it together. So 259A hexadecimal is converted to its equivalent binary, which is 0010, 0101, 1001 and 1010. So this is the equivalent binary value for the given hexadecimal number. Now let us solve one more example with the same procedure. So CAFE dot 3D, which has both the integer part and fractional part. So let us replace with the equivalent values of binary. So for C it is, from the table we can write the values, or you can use the 8421 technique also. So for C it is 1100. We can write that value 1100. For A it is 1010. For F it is 111. For E it is 1110. So for the integer part we have completed. Similarly for the fractional part, for the value of 3 it is 0011. Next for D it is 1101. So we can write that Now just put together all the values that we have obtained to get the equivalent binary, which is 110010111111 triple one zero dot 0011 and 1101 to the base 2. So this is the equivalent binary value for the given hexadecimal value. So this is the procedure that we have to convert a hexadecimal to binary value. Now let us convert a binary value into its equivalent hexadecimal value, for which we have to follow the same procedure as we have seen in the previous video. With a simple change, now we have to segregate starting from the decimal point moving towards the left. We have to split into 4 bits of each. So the first 4 bits will be 1001 and the next set of 4 bits is 0001. So we have to move towards the left, so that is taken over here. Similarly, for the fractional part, we have double 1, but we need 4 binary digits. So remaining 2 has to be filled with 0, but we have to make sure that we are adding 0 to the right side. Only then it will not make a difference. Now the equivalent value is, for 1000, the value is 8. Here also we can use the 8421 technique, or we can simply pick the value from the table. So 8421. 1000 means wherever we have 1, we just have to add it. We have only 1, so which is 8. Next for 1001. So 8 plus 1 is 9. So we have the equivalent decimal value as 9. Next for 1100. So under the 1 we have 8 and 4. So 8 plus 4 is 12. And 1 is represented by C. So this is the value. So for the given binary number, the equivalent hexadecimal is 89.C. Now let us solve one more example. So the given binary number is here, which contains only the integer part. So we have to split accordingly with 4 bits of each. The first 4 bit is split, which is 1110. The second set of 4 bits starting from the right side is 1010. And the third set of 4th bit is 1011. So once after segregating to 4 bits of each, now we will write the equal representation in terms of hexadecimal. So for 1011, using the 8421 technique, so 1011. Now we will just add the values of ones alone. So 8 plus 2 is 10 plus 1 is 11. 11 is represented by the alphabet B. Next for 1010. So adding the values of ones, 8 plus 2 is 10. 10 is represented with alphabet A. Triple one 0. So adding the values of ones, 8 plus 4 12. 12 plus 2 is 14. So 14 has an equivalent representation with an alphabet of E. So for the given binary value, the equivalent hexadecimal is BAE to the base of 16. So this is the procedure to convert any given binary number into its equivalent hexadecimal number.